here is actually one from your homework, but I got a few people asking me questions about it on how to do it. And I figured it was pretty complex enough that it's worth talking about. So just going to run through this real quick. Is the first thing that you want to do, or reading the question says, determine the smallest couple moment, M right here, that can be applied to the 150-pound wheel that will cause impending motion. And it says the uniform concrete block has a weight of 300 pounds. The coefficients of static friction are mu A equals 0.2, so we can say 0.2. Mu B is 0.3, and then between the floor, we're given 0.4 right there. And so essentially, you need to see, look at the system and think about what exactly is going to be happening first if anything were to move in this system. So if we look at it, we could see that the wheel could slip by itself with the moment force and the block not really move. The block could also start slipping this way along with the wheel because the wheel would start rolling and push it. Or the block could tip if the wheel would start rolling and then push it up far enough that it would tip. But essentially, the constant in all of these different cases is that the wheel ends up slipping. No matter what is going to happen, the wheel is going to end up slipping on something. Whether it just slips by itself or if it pushes into the block somehow and moves the block, the wheel is going to end up slipping right here at this point. So the first thing that we're going to want to do is take a look at exactly what happens when the wheel were to slip by itself. And so the first thing actually before that is we're going to draw the free body diagrams of everything. So if we take a look at the box, we're going to draw right in the middle the 300 pounds acting down. And then acting up is going to be the normal force of the box. I'll label it N box. And we're going to give this a distance from the center of X. And then other things we're going to have where these are touching, we're going to have a force here, NB, and that's actually going to be 1.5 feet above ground level on this box. And then we're going to have a friction on the ground, so F box is what I'll label that. And then we're also going to have a friction force acting here where the block is touching the wheel, but I'm going to wait to draw that in a second because I'm not entirely sure which direction to draw it in first. So I'm going to take a look at what friction is on the wheel and then put it in depending on what that is. So if we draw the free body diagram for the wheel, we're going to have going down in the center the 150 pounds, and then going around the circle is going to be the moment couple. And then we have the normal force pushing in, NB, so it's going to be pushing on the wheel at the same part, NB. And then this is where we need to think about where the friction is acting. So if the wheel is going to be kind of turning around this way, let's say it's going in a counterclockwise direction. If the wheel is going in a counterclockwise direction, at this point here, it would be moving down, which means the friction would be acting up on the wheel. Does anybody have any questions about that? Okay, just remember that friction always tries to oppose the motion. And then you just kind of isolate the part there. So, good morning. We're going to go ahead. So these are free body diagrams. We've still got the normal force on the ground, which I'll label as NA, because we got point A here. And then again, we need to say which way friction is going to be going. So if the wheel is turning this way, if it goes this way down at the bottom, the friction is going to go toward the left. So FA is going to be like that. And that should be everything you need to know from those free body diagrams, looking at this. So once we've got our free body diagrams written out, we can start writing the equilibrium equations. And we're just going to go ahead and write everything out that we know, because it's kind of hard to see exactly what we need to solve for.
The friction onto the box as well, or would it only be on the wheel?
Are you talking about? Oh, yes. My bad.
Opposite, or is it going to be the same?
It's going to be opposite. Yes. Thank you. That's what I was waiting to put it on the wheel to put it on the box, and I just forgot. So thank you so much. Yes. So friction on the box is going to be equal and opposite to the friction on this wheel here at B. So make sure you include that and not forget it like I did. So thank you again. We'll go ahead and sum the forces in the Y. And we're looking at the wheel right now. So sum of the forces in the Y, we're going to have FB plus NA minus 150. And that's all equal to 0. Next, we're just going to go ahead and sum the forces in the X. And in the X, we're going to have NB going to the right and FA going to the left. So NB minus FA is equal to 0. And then the sum of the moments about, I said O, the origin here. It's going to help us isolate this moment here. Sum of the moment about the origin, we're going to have M. And then the only other forces causing moments would be these friction forces. So we're going to have minus FB times, and the radius of this is 1.5 feet. So 1.5 minus FA, 1.5, and that should equal to 0. And those are our three equilibrium equations looking at this circle here. And so once we have those for the circle, we can go ahead and take a look at the ones for the box. I'll just go ahead and draw an arrow down here. And so if we look at the ones on the box, we'll start with sum of the forces in the Y again. And we're going to have the normal force N box going up and 300 pounds going down. So we're going to have N box minus 300. And then friction force at B is also going down. Minus FB is equal to 0. Next, we'll have the sum of the forces in the X. And in the X, we're going to have F box going to the right and NB going to the left. And those should be the only forces there. Equals 0. And then the sum of the moments. And looking at this, we have a lot of unknowns in this problem that we're trying to solve for and eventually get. So when we sum the moments, we want to sum it about a point that'll get rid of a couple unknown forces for us. Just looking at it, I think the best place to solve or sum the moments is about this point here, point B, because that eliminates FB and NB for us. So that's the way I did it. You probably could end up solving it for the moment, let's say maybe about this point here, where the normal force of the box is and all that. But that might get kind of tricky because you don't exactly know where the normal force is going to be acting. So right here we know the exact distance of where it's acting and everything in relation to that. So some of the moments about B, we're going to have the first thing that we can look at is this normal force about the box. And so we're going to have N box, and its distance is going to end up being from the box, or from the edge of the box to the center is 0.5 feet, because the entire dimension is 1 foot. I should have drawn that in. And so 0.5 feet. So the distance is going to end up being 0.5 plus x is the distance there, and that's the moment from that. Next, we're going to have the force of the box here, and again this is 1.5 feet down, so, and it's going to be positive. One thing about this is actually going to be negative because it's going to be going in the clockwise direction around that point, and so the force of the box is going to be positive moment, 1.5. And then lastly, we've got this 300 pounds acting on it 0.5 feet away from this box here, so it's also going to be positive. So we've got 300 times 1.5, or I'm sorry, 0.5, and that should all equal to 0.
Hey, where does that X come from?
This X, I just labeled it here kind of arbitrarily. Essentially, the logic behind it is if we have this normal force pushing on this box here, that means that the normal force on the bottom of the box is going to end up being somewhere along here. If there is no normal force here, then the box is going to be completely centered, and so is the normal force, so x would be 0. And so we can account for that. But if for whatever reason the normal force is huge, x is going to be right on the edge, and the box would be tipping. So And we're just kind of leaving it a variable right now just so we can take a look at it. And so, like I was saying at the very beginning, we've got three cases, is if the box slips, the box tips, or if the wheel by itself slips. But no matter what case we're looking at, the wheel is going to slip in anything. So it's important that right now we just take a look at if the wheel alone slips. So if the wheel slips first, and if the wheel is slipping first, then what we can take a look at, or what we know, is FA and FB both have to be maximized because it's overcoming both of these forces. So we know that FA is going to be equal to mu A times NA, and that's going to end up being 0.2 times NA, and then FB is going to be mu B times NB, and that gives us mu B right here, 0.3 times NB. And then this is where we need to get, we need to start substituting some things into our old equations here. So if we look at these equations that we have up here for the wheel, we have FB, NA, NB, and FA, and then moment. And that essentially gives us 5 unknowns that we're trying to solve for. But when the wheel is slipping, we end up having ways to write FA in terms of NA, or writing the friction forces in terms of the normal forces. And so when we know that, we can end up substituting in here for the friction forces, the normal forces, and that reduces our 5 unknowns to 3 unknowns. And that makes it solvable with just these 3 equations here. So I'm going to go ahead and rewrite these equations up here that we had with the friction forces that we know. So sum of the forces in the y is going to be equal to, so FB is 0.3 NB plus NA minus 150 is equal to 0. So Fx is going to be equal to, we're going to have NB going to the right, minus FA is equal to 0.2 NA. That's equal to 0. And then we've got some of the moments about the origin, which is going to give us M minus, for FB, it's 0.3 NB times 1.5, minus, for FA, it's going to be 0.2 NA times 1.5. And that's all going to equal 0. And then this is where we need to take a look at solving basically a systems of equations. So if you look at these 2 equations here, in the Fy and the Fx, they both have the same 2 unknowns, NB and NA. And so I'm not going to do the work for you guys up here. But if we were to solve for them with 2 equations, 2 unknowns, we're going to end up getting that NA is equal to 141.5. and NB is equal to 28.30. And if you're still kind of confused, essentially what we do is we'd put NB in terms of NA. So in this case, we'd probably add 0.2 NA to this. So NB would be equal to 0.2 NA. We would then take that and put it into the equation up above and just solve this in terms of what NA is by itself. And then doing that with these knowns here, we can plug them into this moment equation here, and we end up getting that M is equal to 55.19 pound-feet. And that's one of our options, because again, this question is asking for the smallest couple moment that can be applied that will cause impending motion. So this is what impending motion of just the wheel by itself looks like. So this is where we need to take a look at what our other cases are and try to see, is the moment going to be bigger or smaller in those cases. And so we're not going to kind of look at these in the normal sense of how I normally would. I'm not going to solve for M in these. There's a couple other things that we can solve for that should show us that the moment force is going to be bigger. And so essentially we know all these things here if the wheel were to slip by itself. And so we can go ahead and use these values into the equations we have for the box here to solve for basically the conditions of the box. So if we take a look at this first equation, we're going to get the sum of the forces in the y. We're going to have the normal force of the box minus 300 minus 0.3 NB is equal to 0. And then we can substitute in what our NB is from before, so that the normal force of the box is equal to 300 plus 0.3, and the normal force of the box is 28.30, and we end up getting 308.49 pounds. And so that's what the normal force of the box would look like if the wheel were to slip, just as we have before. Next, we can take a look at the friction of the box down here. So friction of the box minus NB, that's essentially going to be equal to what NB is. So the friction of the box equals NB is equal to 28.30 pounds. And then lastly, we can solve for what this x value is going to be in the case where the moment is equal to that. So solving for the x value, we've got negative 0.5 plus x times the normal force of the box, which the normal force of the box we have as, I'm just going to go ahead and write it in, 308.49 plus 1.5 times the friction force of the box, so 28.30, and then we've got the 300 times 0.5 from before, and that's all equal to 0. And solving for that, we end up getting that x is equal to 0.1239 feet. Okay, any questions about that so far? So essentially, we found what these values would look like if the moment force is equal to this part, if the wheel slips first. Now what we want to do, the reason why I found these forces for us here, is we want to see what these would look like in the event that the box were to slip or to tip. So maybe if I said it just like that, it doesn't make sense. But if I write it down here and we analyze it a little further, hopefully you'll kind of see why. So I'm going to go ahead and take a look at the case if the box were to slip. So if the box were to slip, we would end up having that the friction force of the box is equal to mu times the normal force of the box. And so I'm going to go ahead and use the normal force that we found before, the 308.49. And this mu here is going to end up being 0.4 like they gave us up above. So we're going to have 0.4 times 308.49. And multiplying that out, we end up getting 123.4 pounds. Now, when we get that value here, we end up finding that the friction force of the box is a lot larger than it would have been earlier with just this moment equaling 55.19. So this essentially tells us that the box is going to end up, if the wheel were to be slipping in this condition, the box is going to end up staying put, and that it would take a lot of friction to get the box, a lot of force to get the box to start sliding. So that tells us that the box is not going to slip before the wheel slips. Does anybody have any questions about that? And then the next thing we need to look at is if the box were to tip. And so if the box were to tip, really the impending motion that we have on that is if the normal force would be right on the edge of the box here. If we were to take a look at it here, that would mean that x would equal to 0.5 feet. It'd be right on the edge and the box would be right there tipping. Well, if we write that down, 0.5, x equals 0.5, again, we found that if the wheel were to be slipping, x is going to be equal to 0.1239. And so, because it's greater than 0.1239 feet, that means that the box is not going to be tipping if the wheel's slipping first. So, hopefully that made sense. The way that you need to solve this problem is a little different than you would before, but you need to essentially look at all the conditions that would be happening, and you need to know that the wheel is going to be slipping in all of these conditions here. And so, using that, if the wheel is slipping in all these conditions, we can solve for what the values would be if the wheel is slipping. And in the case here, all of those values while the wheel is slipping end up being smaller than they would be if the box were to tip or to slip. So that's essentially how you'd go about solving for that type of problem. Does anybody have any questions about that? Okay. This one was a little more conceptual than what you'd see in your exam, I would assume. And so it's not a bad thing to look at these types of problems, but I would say you'd probably expect something a little less, complex as this. So we're working on belt friction here. We can go ahead and read the question. So it says the horizontal force of 810 newtons and a counterclockwise couple moment of M are applied to the axle of pulley A, which is supported by a roller. So this whole pulley right here. The coefficient of static friction between the flat belt and each pulley is mu equals 0.4. So 0.4. Write that down. The radius of each pulley is 40 millimeters. Determine the maximum value of M and the corresponding tensions in belt segments AB and AB prime. So we got AB and AB prime down here. Answers must be supported with relevant free body diagrams and equilibrium equations. And so essentially what we're trying to do is we're just trying to solve for all the values here. And so we need to make a free body diagram to do that. We're going to go ahead and draw the free body diagram for this pulley here at A. And that's our first step right there. I'm going to go ahead and draw off to the side over here. So, oh my God, that's a really good circle. Okay, so we've got, at this here, we've got the axle in the middle. And so the axle in the middle, first thing I want to say is pin is a roller connection. So we're going to have AY going upward on it. And then there is no AX because it is just a roller. So rollers are just vertical. We do, however, have 810 newtons acting to the left on it. And then also on this pulley, we've got the moment going in a counterclockwise direction. And then we're also going to have the tension forces of the belt pulling on the top and the bottom. So we've got tension AB and tension AB prime. And those should be everything that we need on our free body diagram for this pulley. And I'm just checking to make sure. And then, of course, you can always just write mu equals 0.4 above it, just so you know. And so this is where we get into some... Oh, one other thing is we want the radius. So I'm just going to write r equals 0. What is the 0.04? 0.04 meters. Okay, and that's everything we need for our free body diagram. Now this is where we get into some new concept stuff. And so in your lectures, I'm not going to talk about how to derive them or anything, but in your lectures you should have gotten told about an equation where it's T2 over T1 is equal to E to the mu s times beta. And it sounds like a whole bunch of gibberish. Basically what that's saying is that if you're looking at something like this and there's friction in the pulley, one of these tension forces is going to be bigger than the other. And so this is essentially telling us that the bigger tension force divided by the smaller tension force is going to end up being equal to E to the, and this value here is going to be the static friction of the belt and the pulley, and then this is going to be the angle that the belt is on the pulley. And so these are some unknowns. So mu s equals friction coefficient, and beta equals the angle touching pulley. Essentially, that's the contact or whatever, the angle around the pulley that the belt has contact with. And it needs to be in radians. That's a huge important part of that, is it needs to be in radians there. And then T1 or T2 is going to be greater than T1. And so we're going to go and see how this equation really applies to this situation. I'm going to go ahead and rewrite the equation over here as T2 is equal to T1 times that E to the whatever. And so you essentially multiply both sides by the T1, and that's what you get this equation here. Now, we need to know out of these two tension forces that we have, TAB and TAB prime, which one is going to be the bigger value? And that's where this gets a little tricky and a little bit more conceptual. Need to be careful with what you're looking at. But essentially what we're looking at is we're trying to see essentially if these are kind of slipping on this pulley here, and what direction this belt would be kind of slipping on this pulley, or it would slip if it were at impending motion. And so if we take a look at the way this pulley is moving, it's got a moment force, or a moment applied to it in the counterclockwise direction. And if it's going in the counterclockwise direction, just to kind of look at it, if we were to look at this belt and assume that this belt here were not moving and that the moment force itself were causing the pulley to move, the way it would be slipping is it'd be slipping in a way that this force would be staying here. I'm not really explaining this well, am I? I'm trying to think of a better way to explain it. Essentially, scrap that idea. Instead of this pulley moving, kind of conceptualize it as if the pulley were staying still and the belt were moving around it. Because ultimately it's kind of relative. If the pulley were to be moving this way and we assume the belt were to be staying still, we could kind of see maybe how the belt would be staying on it. But instead, if you take a look at if the pulley were staying still and the belt were to be moving in that way. So kind of trying to compare it and make it more relative. If the belt were to stay still or if the pulley were to stay still and the belt were to be moving on it, it's kind of a similar way to how it's going. The belt would end up moving on the top part here. Does that kind of make sense? It's kind of hard to visualize, like I was saying. But essentially, it's relative. Does anybody have any questions about that so far? I'm sorry I'm not really explaining this too well. It's getting a little bit deeper. Essentially, I'm going to try like an example on this. So if we were to try to take a look and assume that this paper were the belt and that this Clorox tin thing were the pulley, we're trying to look at it in a situation where this pulley would be moving. So the pulley is going to be moving in this direction here, and the belt is going to be stationary. Well, essentially, I'm trying to look at it in a way that if this pulley were to stop moving and the belt were to move around it in the same way, the belt is going to end up moving with the top part going out. Does that make sense when you kind of visualize it like that? Okay. Sorry I couldn't explain that very well on paper. I didn't really know exactly what to say. But essentially, if we were to look at it like this pulley were to stop moving, the belt would be moving on the top. Well, if the belt were to be moving on the top in a case like that, that essentially tells us that this tension force on the top here has to be greater than this tension force down here. And the reason for that is if they were equal, then the belt would not be moving at all. But since the belt is moving and it's moving favoring towards this, that means that this tension force up here is going to be bigger than the smaller one. And if we were to kind of put that into relation of these two belts here, that tells us that tension AB is going to be greater than tension AB prime. And so knowing that, we can go ahead and put that into our equation. And so since we have T2 is greater than T1 in this equation, we can write that TAB is going to be equal to TAB prime times E mu S beta. All right, and that's how we frame it in our equation. Now we're also going to want to look at our equilibrium equations on this free body diagram here. So we can go ahead and take a look if we were to sum the forces in the x. So summing the forces in the x, we end up getting TAB plus TAB prime minus 810 is all equal to 0. And then we can also sum the moments about the origin. Summing the moments about the origin, we get that the moment force is equal to minus TAB times 0.04, and then plus TAB prime 0.04, and that's all equal to 0. Okay, and now we have all these equations to solve for what these values are, because as they were asking before, we want to know what this moment force is here, and then what the tensions in the belt are as well. And so doing that, we essentially, what we need to do is we need to solve for TAB or TAB prime. Well, we have this equation here that puts TAB in terms of TAB prime. So I'm going to go ahead and take this equation here and substitute it in for TAB over here. And so rewriting that, we get the sum of the forces in the x is equal to TAB prime times E mu s beta plus TAB prime minus 810 is equal to 0. Okay, and doing that, we can go ahead and solve for TAB, knowing what these values are. Now, it's important that we take a look at what these exponents of E would be. And so mu s was given to us up above. They gave it to us as 0.4. So that one's pretty straightforward. Typically, they would give that to you in the problem. Now, beta here is where it gets maybe a little bit more confusing, especially in different problems. This one's not as terrible. But we're essentially looking at what angle the belt is having in contact with the pulley here. So if we were to take a look at what's happening on this pulley here, we can see that the belt and the pulley make contact at about this point right here. And the pulley and the belt are in contact with each other all the way up until the top of the circle right here. So we essentially have this whole angle here that we want to take into account for as beta. Well, looking at that, we can see that beta ends up being half the entire angle of the circle. That's half the entire angle of the circle. And so we can see that beta, knowing that, would just be pi, because 2 pi is the entire angle, and so half of it is just pi right there. So we can go ahead and write down below beta is equal to pi. And so I'm going to rewrite the equation one more time with our known values in there. So we've got TAB prime times E 0.4 pi plus TAB prime is equal to 810. And that's just rewriting that. And then you can go ahead and just solve for this like you would in another algebraic problem, and you'd end up getting that TAB prime is equal to 179.46 newtons. And that's one of your answers that you're trying to solve for here. So for TAB prime, you get 179.46 newtons. The next thing that you'll want to take a look at is what TAB is going to be. And this is where you're going to substitute this value in for one of these equations. You have a couple of options here. I substituted it into this equation here. So TAB is going to be equal to 179.46 times e to the 0.4 times pi. And doing that equation, we end up getting 630.54 newtons. And that's another one of our unknowns here. And then lastly, we want to solve for the moment force. And the moment force required us to know what the tension force in both of these segments were. So we can go ahead and substitute in these two values we knew, or that we found, into this equation here. And we end up getting m minus TAB was 630.54 times 0.04 plus, and then TAB prime was 179.46 times 0.04, and that all equals to 0. And then again, solving this algebraically by adding and subtracting from both sides, we get the moment force is equal to 18.04 Newton meters. And that's what we get up here. And that's how you go about solving a problem with belt friction like that. Essentially what we're looking for here is we were solving for the maximum that M could be if this were to slip. So this is essentially right on the verge of slipping. That's what we were taking a look at. And right on the verge of slipping is when the friction in the pulley would be equal to, or it'd be equal to whatever this is, and then we can use this equation here. And so we can solve for what these values are here using our equilibrium equations and then this equation here. Does that make sense? Does anybody have any questions about that? Okay. I apologize that I wasn't the greatest at explaining this problem. It's a little bit more conceptual than what I'm used to talking about. But if you guys have any questions later on, that's all I have for you guys today. So you can come up to the front. Go ahead and leave your quizzes here on the table for me, and I'll look at those. So if you guys have any further questions, you can come up and ask or email me later. But thank you.